Hi, Leonard here. Um, this is just for fun. We've been through the grim and terrible stuff. All we really have to do, there's some more I could talk about, but I could not support it with good data, so I'm going to let it go. And we're talking about treating the universe like a big puzzle. How could it work, minimizing the amount of magic we have to introduce? So, went through it once and showed you all the difficulties, and now here comes how we try to resolve them. The picture, by the way, is by, in quotes, Gustave Doré. Um, it's an illustration of the raven. Having looked at a number of illustrations of the raven by Gustave Doré, first off, it's fabulous artwork. Second place, it's not all done by the same hand. He had a whole stable of people whose job was to do the technical stuff. And that meant he would do a sketch handed to somebody who'd then spend, months like on one picture, or maybe three or four people. They were the ones who really put the expression in, the art of it. Doré really was just doing the composition. But I think the end result is just marvelous. So I'm still using Doré's um, work for introductions, even though we're not really all that grim. Yeah, you could get grim about it. Um, uh, there's nothing, you can always find some reason to be unhappy. Um, but, this is either true or it isn't. If it is true, there might be some engineering principles we'll not be going into. This is just we treat it as a puzzle. All right, so we build a universe, and we'll start out. I want to show you a frowny face, like uh, this one. All right. That means we've not done what we wanted to do. That means we have to introduce a contradiction, some magic, something that's weird. Try to minimize that, but we're going to need to introduce some stuff that's just not, doesn't follow from previous descriptions. Um, all right. Won't have now. So to start out, our magical thing is you're going to lend me a neutrino. I used to amuse myself by trying to figure out how, if you converted a neutrino into energy, how far it would lift an ant running across your tablecloth. It won't lift him very far. Um, but that's what I need. I need not a neutrino, a neutron, plain old neutron. I need to borrow one. I won't need it long, but I'll need it. And this introducing the neutrino is kind of magical. All right, so we assume there's nothing. Uh, and that's the whole point of, we call this nothing out there. It's just a name for now. So what is it like out there? Well, first off, there's no matter. Okay. There are no rules of logic because you can't have logic without a universe to be logical about. Any logical argument will start with the assumption that there is something, at least all the ones I've heard. All right, no logic, no matter. There are no dimensions. Potential dimensions, yes, but there's no such thing as distance. Time is undefined. That being the case, we're going to arbitrarily set time at 0, and it's not going to be going forward or back. That's just the way we're going to set it. and there's no moral order. There's no good or bad. There isn't anything. So, we take your neutron and set it loose. It follows an irregular course. Why? Well, we can see that in a minute. The places where it bunches up tend to pull the path of the neutron by gravity. So you lent me gravity when you lent me the neutron, of course. Neutron has mass. The reason all neutrons are alike is it's all the same neutron. Got that? It's going back and forth in time, yeah. We haven't defined time yet. We will soon. Eventually, neutron flies right up its own tailpipe. Now I can give it back to you at exactly the time and place you lent it to me. Let's say the path of the neutron looks like this. This is oversimplified. All right, we'll say, just for argument's sake, all right, we've disappeared. Hang on. Okay. There we are. These two triangles here, this is where you lent me the neutron. It followed this path. Eventually, after an enormously long complex route, it comes right back to where it was, and I give it back to you. So that's where the exchange takes place. Otherwise, all right, the two triangles where you gave me the neutron, and then that's also when you took it back. The path is clumpy because the neutron has gravity, tends to pull the neutron, the path of the neutron, into a place where there's already a bunch of neutrinos, right? That's why we get clumps, pulls the path of the neutrino toward itself. Every now and then, the neutron was going to decay into a proton and an electron. That's the nature of neutrons, and that can reverse. So that goes back and forth. There's not much matter because neutron you lent me there's not much antimatter. One of the big puzzles is, why is there matter and not antimatter? And they come up, with semi-magical explanations. We started out with a normal neutron. That's why the universe is almost all matter. If there were antimatter out there, we'd have a problem because from time to time, a matter star would hit an antimatter star, and when they annihilated each other, the energy would sterilize that galaxy for a long time. Okay, we've got collections of mass. Now we can define time. Given some mass, you can define time. Okay, let's say you're looking down at something heavy. You're up there. Now don't confuse in here and out there with up there and down here, right? Up and down, in and out. Now I'm on the bottom, shining a light up at you, right? Here's this massive object, planet or star or what have you. Could be a whole galaxy, and I'm just among them. And I'm shining my flashlight or laser beam, or whatever, up at you. Now, when it leaves me, that beam of light has a wavelength, which is very short because it's pretty energetic, As it climbs, you remember E equals mc squared, costs energy for the photons to rise away from a mass. Um, that's relativity, and we pretty much have to believe that one. So that means down here, the the photons are going bip 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 bip, and up here they're going bip bip bip. So I'm down at the bottom, you're up there at the top, and as you look at me, you count the wavelengths of photons going by, and you are convinced that time is going slow for me because I'm down a gravity well. Now then, uh, if that wiggle comes to a stop, if the gravity well is, as it were, deep enough, then time has stopped for me as seen by you. Okay, so that all it means is there's a tangle of neutrons and protons and electrons. So dense that the light can't get out at all because as it climbs out of the gravity well, it eventually has no, can't wiggle at all. Now that's what we call a black hole. We're going to make our black hole three-dimensional. Could be any number depending on the potential number of dimensions in the nothingness we started with. Okay, now then we can define time, the difference between in here and out there. All right, there it is, all laid out for you. I don't want to make this too complicated. In here, we're looking down a gravity well, or we are in a gravity well, and time is going slow. Out there, we're at a distance from the nearest gravity well, and time is going faster. Remember, we started at time was set at 0, not going any direction. Now we have time going one direction inside our black hole and the other direction outside, because it has to all cancel out. So out there, time can wander any direction it likes. Here, looks like we're away from clumps, or here, and time is going to be going in the opposite direction for what it is inside the black hole. This is the out there, right? Over here, where there's another clump, well, a lot of times likely to go in the same direction. But we're stuck in here. We can't get a signal out, and really no signal can get into us because the edge, the stuff falling in is falling at the speed of light. So you can't beat that. All right, out there, time can go any direction, in any place. On average, it'll be slightly opposite of the time in here, but in here it has to move always in the same direction. Can't go back and forth. Out there it can go any direction. In here it goes only one direction. In our black hole, the contents are being compressed, they are contracting. The gravity well is getting ever deeper. We will now say that out there, time is moving forward, while in here, it's moving backwards. They're just names, okay? Not only can nothing get out, nothing can get in. So in here, we are truly isolated. No contact with the outside universe. Of course, it all has to wind up crunched up in the middle eventually. As the gravity well gets deeper and deeper, all this gets more and more compressed, contracted. eventually winds up as being, it just gets smashed into oblivion. Um, all the laws of nature, all the characteristics, or many of the characteristics of that neutron get wiped out because the intense heat and pressure as the universe crushes into the center. Oh, did I mention? Yeah, that's right. That's our universe. Um, just it's like you leave a thermometer in a car, right? And you close it, leaving the hot sun, and the old-fashioned thermometer heats up until the alcohol busts the top off, and then it gets hotter and hotter, and then the little glass tube the alcohol was in melts, and the little cardboard backing it sat on gets scorched down to an ash. I mean, as it gets hotter and hotter, all the rules are broken. If the thermometer was supposed to tell you the temperature, but at a high enough temperature, can't do that. So as the thermometer melts, as it were, um, the bottom has fallen out of the universe. Um, uh, so there was no Big Bang. Forget it. That's ridiculous. It can't get out of a black hole. We saw that. All but in here with time running backwards, it looks like it began with a Big Bang, but it's going to end in a big crunch that happens, if you calculate it, at exactly the same time as the Big Bang was supposed to start. So there's our first success. Given nothing and the loan of one neutron for an infinitesimally small period, we can build a whole universe. It follows the rules of one way of all time in all directions, moving steadily in one direction. Up, left, right, forward, back. All of those directions of time move in one direction as you move toward the big crunch. And you don't have to invent some way of exceeding the speed. Well, that's what they did, you know. I mean, they calculate, oh, well, the universe began, it started, then suddenly the laws of nature formed. And when they did, it was like you took a pencil, right, to take this drumstick, right? We can balance it, right? And right now it could go any direction, more or less. But bingo, now it's going in one direction. It has lost opportunities, and that released energy. And that's what happened. The laws of nature, the properties of a neutron, could have been anything. But once it happened, once there was the great observation that nobody ever talks about, then that released energy, and that fueled the expansion of the universe. Oh, which warped space. Wasn't really, we weren't really exceeding the speed. It's don't have to do any of that. Give me a neutron and empty space, and I will build everything the Big Bang accounts for. When we'll go on in the near future. With anything like luck, I shall be able to find my cursor, and you know what to do. I am going to try to magically turn the session off. So come back next time, sometime in the future, we will carry on.